This is the 12th in the series of videos on the Control101 MATLAB toolbox. Here we're going to look at an introduction to frequency response. So, for some reminders, the community has agreed on an outline structure for a Control101 course, and the MATLAB Control101 toolbox has been developed to support such a course. The tools enable visualization and support tedious number crunching requirements so students can focus on core concepts. This video is going to focus on introducing the concept of frequency response, which is a cornerstone of many control design methods. So what is frequency response then? Look at the picture we've got here. We're going to consider the response of a system G of S when excited by a sinusoid. So you can see the input signal is d sine omega t, and the output signal is given as dA sine omega t plus phi. So if we sketch the input u and output y on the same plot, what will you notice? Okay, so let's look at this in more detail. Both the input and the output oscillate at the same frequency. You can see here given as omega. The gain A is the ratio of the output magnitude to the input magnitude. And the phase phi is the phase difference between the input and the output. A convenient observation is given here below, but we're not going to dwell on that in this particular tool. So here's an illustration of an input and output for a given system G, and what you can see is the output line blue clearly has a different magnitude from the input line red, and also it has a phase shift. By the way, don't look around t is close to 0 because there'll be transient effects which are not part of the frequency response. So the frequency response app allows users to explore this then. So how do gain and phase depend upon both the system and the frequency? And how are they computed from time domain plots? Let's show you the app then. So we'll go over here to this screen and bring it in. So here's the app. Hopefully you can all see that clearly enough. And what you'll notice is Y is in blue, U is in green, and we've also added the potential for a system with a delay, which is a real sort of system uncertainty, and that's the greened dash line. Now these bottom two plots are zooms. So if you look at the time scale, you'll see the time scale on these bottom plots is a lot smaller than the time scale on the top plots. And in fact, these dashed black lines here show you where the zoom has been taken. Now, the left plot focuses on the input, so you'll see it's normalized around the red line, and the right plot focuses on the output, so it's normalized around the output. And that's so you can zoom on different features just as you need it. So let's see what happens then if we change frequency. I'll go from 2 to 4. And you can see that the amplitude has changed significantly. What if I go from 4 to 6 and update the figures in the data? And again, you can see the amplitude has changed significantly. What if I change to a different system? So let's take this system here, 2 over s, s plus 1, s plus 2. Sorry, 1 over s, s plus 1. Update the figures, and what do you notice? A very different plot. Change the frequency again, update the figures, a very different plot. So what you can see is as you change the system, as you change the frequency, you get very different gains and phases. Now, if you actually want to work out what the gains and phases are, that's what these zoom plots are for. So the red line, the input, is always normalized to 1. And so the gain is basically the amplitude of oscillation of the blue line, and you can get that from this bottom plot. And you see conveniently it's drawn this sort of pink arrow, so you can see twice the amplitude. And if you want to get the phase shift, you'll see points of corresponding phase are shown. T1 for the input in the left-hand plot, T2 for the output. And you'll see the times are given here in the left-hand purple boxes, so you can actually work out the time shift and then using the frequency work out the phase shift. Now finally, What's the impact of a delay? Let's add a 0.2 second delay and update. And you can see if you have a delay in your system, then now the output is slightly delayed. And as a consequence, the times are changed and the phase difference changes. And you'll see that in this pink box here. I can make the delay bigger and you'll see the phase shift changes. So you can do that for any number of systems that you like. Let's choose that system there. And hopefully you get the point. So the app allows you to explore different systems, different frequencies, different delays, and how do I actually determine frequency response from that. So some conclusions. We demonstrated how to run and use the frequency response time behaviour app in the Control101 toolbox. And you can use this in lectures to illustrate things to students, or just give it to students for their own private study. As ever, there is a manual which contains links to some MATLAB source code, and the manual will open automatically when you run the app.